So, hello, and I suppose, good morning, everyone. By the time that I'm recording this video, it's almost like 1 a.m. in the morning. So, actually, I was supposed to make another video, and that was regarding differential equations, but I don't think I have the time tonight to record it, since I'm also recording this video, and I have to go to the campus later to attend to some important matters. But nevertheless, looking on the bright side, we are recording this video now, and that's a good thing. So, without further ado, let's get to these problems that is basically the homework for our statics of rigid bodies course. And I hope you, as you're watching this video, I hope you grab your calculator, your pen and your paper or your notebook, whatever you're writing on, and I want you to solve along with me as we do these problems, okay? So I kind of have to do these quickly since I only have like around 3 hours of sleep left when I'm finished with these problems. So let's start. So our first problem states that a concrete column has a diameter of 350 millimeters and a length of 2 meters. If the density of concrete is 2.45 megagrams per cubic meter, determine the weight of the column in pounds. Okay, so let's apply a bit of analyzation in these problems. Okay, since actually before we start, I took a bit of notes regarding what we have currently discussed so far in the course so that I can explain in depth about the things that we're going to solve, the strategies that we're going to apply in solving these problems, all that good stuff. So, going back, in this problem, we are given a column, and when we're given a column, as you may have encountered in your physics course or even your calculus courses, a column would commonly denote, in geometric terms, a cylinder. Okay, so let me make quite a bit of a rundown cylinder here. It has a diameter of 350 millimeters. Okay, 350 millimeters, and it has a length of 2 meters. Okay, and we're also given the density of concrete, which is the material used in making this column. Okay, so let's denote density in raw. Okay, so it's like a P, and its density is 2.45 megagrams per cubic meter. Alright, now that we have kind of visualized what we're trying to solve in this problem, let's try to convert the units into some more comfortable ones that we can work with. So we can convert this millimeters into meters. So 350 millimeters is 0.35 meters, since there is 1000 millimeters in 1 meter. Okay, and as for megagrams, 1 million grams is equal to 1 million grams, yeah, is equal to 1 megagram. So we can denote this as 2.45 times 10 to the 6th power, since that would make it in the millions. That would, yeah, grams per cubic meter. Okay, now that we have consolidated our units into something that we can work with to solve, now we have to consider what is asked of us. So we have to determine the weight of the column in pounds. Okay, all right. So we need to analyze uh, what can give us the weight of this column, okay, this concrete column. So first, we have to look at this formula. We know that density, let me write it down, we know that density is equal to mass over volume, okay? And we can solve mass from there. How so? We can derive the formula, let me do it real quick, by multiplying both sides by the volume. So we can cancel both of these and we'll be left with the mass on the side, and we are gonna have this equation that says that a mass is equal to the density times the volume. And from the mass we can get the weight. Alright? Since if we're given the mass, we can compute for the weight given the formula. Weight is equal to mass times the gravitational constant. So that is basically the analysis of what we're trying to do in this problem. Okay, so let's keep these here for now, and we'll be trying to solve for these problems. So first, we have to get the volume, since we're given the density already. Okay, we're given the density. So how do we compute for the volume of a cylinder? Well, you have to recall your geometry that states that the volume of a cylinder would be equal to pi r squared times the height. Okay, and of course you can modify this formula, and that is what we're gonna do for this video. I'm gonna use the formula volume is equal to pi diameter squared over 4 times the height. So that is basically the same if you're trying to do the radius of the cylinder, since the radius is just half of the diameter. Okay, so let's try to solve for the volume of the cylinder. So we have pi, and then we have our diameter 0.35 meters. This is gonna be squared, okay, over 4 times the height, which is 2 meters. Now you can plug that in to your calculator and then solve for it, but that will give you the value of let me just write down the whole value. And one more thing to note, I'm only going to round off the final answer for this problem, since we're trying to be accurate with our answers. So the answer is 0.19242255 cubic meters, since we square this meter and then we multiply it to another one, so that makes it cube. Okay, and now that we have that, we can substitute that, or I mean we can substitute that to our volume here. Okay, so let's do that here. So we have our mass, and that would be equal to the density 2.45 times 10 raised to the 6th power grams per cubic meter. Okay, let me do that in a way that it kind of fits. Okay, times we plug in the volume. So let's just put in this value here. cubic meters. And based from this, we can cancel the cubic meter, and we'll be left with grams, which is the unit for mass. And you can plug this in your calculator, and your answer would be 471,435 point. Okay, let me do that again. 0.2475 grams. Okay, and let's convert this into an easier unit, that would be kilograms. So we'll just do a bit of dimensional analysis. So we can multiply this by 1 kilogram, which is basically 1000 grams. Okay, and then we can cancel grams, and if you want to, you can just do it like this and you end up with the same answer, but we're showing the complete solution for this one. So I'm basically having 471.435 2475 kilograms, and this is our mass. Okay, this is our mass, and we're not rounding off yet since we want to get the most accurate answer that we can for this. So let me make another slide. Okay, and now using the other formula, which is weight equals mass times the gravitational constant or gravitational force, we can compute for the weight. So that's 471.435 2475 kilograms, okay, times 9.81 meters per second squared. Okay, and when you multiply that, we know that kilograms times meter per second squared is the SI unit for newtons, which is force. Okay, and it's also the unit for weight, since that is influenced by gravity. Okay, so we're gonna end up with 4624 point. We're gonna have more decimals here, 779778 newtons. Okay, so that is basically our answer for this one. However, we are asked to get the answer in a specific unit, and that would be in pounds. So we are currently in newtons, so we're gonna convert this into pounds, and in 1 newton there is approximately 0.225 pounds, and we're gonna do a bit of dimensional analysis with that. Okay, we're just gonna do conservation of mass for this one. Okay, so that we can cancel newtons, and then we can multiply this value to this value, and we'll end up with the answer in pounds. So the weight would be 1040.57545 pounds. Alright, and finally we can round off. So we can say that our weight is approximately 1040.58 pounds. And so we can finally say that The weight of the column in pounds is approximately 1040.58 pounds. So if you were solving with me and you got the same answer, that's nice. But if you have a slight error, let's say you have around 1039, 1041, or maybe even a slight deviation in the decimals, that's okay. This is since we didn't round off our answer. We didn't round off until we got the final answer, rather. So that is fine. And maybe on tests, that is fine also, since we don't really have the time to write all those values down and that stuff. So yeah, this is our answer for the first problem. Very nice. Now we will move on to our second problem. If a man weighs 155 pounds on Earth, specify A, his mass in slugs, B, his mass in kilograms, and C, his weight in newtons. If the man is on the moon, where the acceleration due to gravity is 5.30 feet per second squared, determine D, his weight in pounds, and E, his mass in kilograms. Okay, so we have a lot to solve on this one, but it's really easy if you think about it. And that is what we're gonna do here. So first, again, let's visualize what we have. So let's say we have the Earth here. Okay, let me just make a small presentation so that it looks pleasing at least. Okay, let's say this is Earth. Okay. Okay, and we have a man here. And let's make another one. And let's say this is the moon. Okay, let's say this is the moon. Okay, and we have the same guy here. Okay, so for the first part, we're given the mass of the man, which is 155 pounds. And we know that the gravitational constant on Earth is 9.81 meters per second squared, or if we do it on feet, it would be 32.2 feet per second squared. Okay, and for this second part, on the man that is on the moon, he has the same mass, but the gravitational constant would be different this time. It would be 5.30 feet per second squared. Okay, and given these conditions, we can solve for what is asked. So let's try to solve first. Let's solve A first. Okay, we have to compute the mass in slugs. So conveniently enough, one slug is equivalent to 32.2 pounds. Yeah. And why do I say it's convenient? It's the same as the gravitational constant on the Earth, 32.2. So actually for this one, we can just do a dimensional analysis for this one. So we have 155 pounds. Okay, and we can multiply that to one slug, which is the equivalent of 32.2 pounds. Okay, so that's it, and we can cancel these units, and by solving this rather, we will end up with an answer 4.8136 slugs, or we can approximate it further to 3 significant figures for 0.81 slugs. This is what we're going to be using on for the later problems, for the later parts of the problem rather. So this is the first part of the answer. This is the answer for A. Let me do that in blue. Okay. Now we proceed with B. Okay. For B, what we have to do on B is to compute the mass in kilograms. So basically we're converting pounds to kilograms. Yes, you can do it directly by converting pounds to kilograms, but let's do it by slugs this time around. So we have to take note that 1 slug is equivalent to 14.59 kilograms. Okay, and to get an accurate answer, we're just gonna do this. So 155 over 32.2 slugs. Since again we want to have an accurate answer, and we really don't want to take this rounded off value for now, and we want to take this since it has some additional values that I didn't put. Okay, and we multiply this by 14.59 kilograms per 1 slug, and then we can just cancel again. Alright, and we will end up with a long answer again, but I will just round it off. This is around 70, this is approximately 70.23 kilograms. Just put the approximately sign. Yeah, approximate sign. And you can compute using pound to kilograms directly, and that would give you an approximate value of 70.31 kilograms. But for the sake of this problem, we're going to use this value. Okay. Okay. Now let's make another frame, and we will be answering part C. So for part C, we have to compute the weight in newtons. So again, we will use the formula weight equals mass times the gravitational constant. Take note that we're still on Earth, so we'll be using the constant, the gravitational constant for Earth. So we have our mass, which is 70.23 kilograms, times 9.81. Let's just to make it not confusing, 9.81 meters per second squared. And again, this is the SI unit for newtons, and when you compute for this, I'm just gonna round it off. This will be approximately 688.96 newtons. And again, if you get slight deviations in the answer, that's fine, that's completely fine. That's basically the standard in engineering, where we really don't get the exact answer, but we do get close to it. Okay? And now for part D. So we're on the moon now. Okay? So we're right here now. And for part D, we're asked to find the weight in pounds. Okay? Now, I want to reiterate that this might be confusing for some if you are converting directly. If you are converting the feet per second squared into meters per second squared, this is a mistake that I actually encountered earlier as well, because I just tried to let's say I had the 5.30 feet per second squared. I tried to divide it by 3.28 feet something, but that's not really correct since you don't have the per second squared value, so you can cancel. And what you want to do is divide it directly by the gravitational constant as well, so that would be 32.2 feet per second squared. So it's 5.30 feet per second squared divided by 32.2 feet per second squared if you want to do it by the means of meters per second squared, but for the sake of this one, I'm gonna do it the easier way. We're gonna use slugs, okay? Since we know that a pound force, okay, a pound force is equivalent of one slug times feet per second squared. Feet per second squared, okay? And luckily we have the value for slugs, and we also have the value for feet per second squared. Okay, so using the same formula, it's weight is equal to mass times gravity. Okay, so the mass is 4.81 slugs. Let's just use the rounded off value for now, and we multiply that by 5.30 feet per second squared, and that will give you the pound force unit, which is a unit of force in pounds, yeah. And once you multiply that, you will have 25.493 pound force, but for the sake of it, I will round it off again to 25.5 pound force. Let's just put it in pounds. Okay, and if you analyze our answer, the mass of the person is actually greater than its weight in the moon. Yes, that is since, you know, we are 6 times lighter in the moon than we are in the earth. Yeah, if I recall correctly. So that's why you float in the moon, and hence you have less weight. Okay, so that explains, this numerical value explains exactly that. Alright, and that is what I mean by the saying that mathematics is the language of science. And okay, moving on. For E, it is the same as the one we have on B. Yeah, since mass is a scalar and it's constant, so the mass won't change even if you're on the moon. Only the weight, since it is a vector unit and it's affected by gravity. So for our E, okay, the answer is the same. It is 70.23 kilograms. Okay. Okay. All right. Okay, so that is for number 2. Now, number 3 is kind of tricky at first since we don't really have a lot to work with, but if we analyze it, if we can visualize it further, then maybe we'll have a starting point on which we can understand the problem more. Okay? So 2 particles have a mass of 8 kilograms and 12 kilograms respectively. If they are 800 millimeters apart, determine the force of gravity acting between them. Compare this result with the weight of each particle. Okay, so it sounds hard at first, but let's try to visualize it first. So we have 2 particles. Okay. Okay. Let me do that again. Okay. And then another one right here. And they are around 800 millimeters apart. I'm putting this at the center of their mass, since that is where gravity is acting upon, and it would have the gravitational force right here, since they are, how do I say this? They are exhibiting, yeah, exhibiting force towards each other, just like how you would compare our Earth, let's say, to the moon and even to the sun. So that is why, if we look at this, if we look at the end of the problem closely, we are comparing this result with the weight of each particle. So given the weight, that is basically gravity of the Earth. So let's treat this as more of like a free body diagram right now. Okay. So we have force acting downward, that is the pull of the Earth. And let's denote it as mg. Okay. Actually, let's try to make it more clear. This is m1 g, and then m sub 2 g. This would be the mass of particle 1, and this is the mass of particle 2. Okay. Let's just say that the Earth is at the background, like right there. Let's say that the moon is right here. Since you know that we are exhibiting forces when there is a weight to each other. Okay? Kind of like that, if you get what I mean. Since there's a force that's keeping us in orbit, so the moon is in orbit with us, and we are in the orbit of the sun. So if you think about it, that's kind of broad. Okay, going back, if you see our variables, we now know what formula what we're going to use, and that is it is the gravitational attraction formula of Newton. Okay, and its formula is this one. Okay, it's the gravitational constant, universal gravitational constant, times the m1 m2 over r squared. And this is not the radius, but the distance. This is r, which is the distance. Okay, and let's actually try to solve it below here. Okay, now, so let's try to label these first. So this is 12 kilograms, which is mass 2, and mass 1 is 8 kilograms. And the distance, let's adjust these for a bit. That would be 800 millimeters, or 0.8 meters. Okay, now if you are pushing an endeavor in any physics course, the gravitational constant, the universal gravitational constant is 6.67 times 10 to the negative 11th power newtons times meter squared over kilogram squared. And then we multiply it by our m sub 1 and our m sub 2. Let's try if it fits. Probably will. Okay, and then let's put distance 0.8 meters squared. Okay, now let's put a force here. Okay. And let's say that this is attraction. Okay. Now, uh, before you input this in the calculator, let's cancel some units. So we have kilogram squared in the denominator. So we can cancel this, this, and that. And then we can also cancel this since the meter is being squared here and it is also squared here. And finally, we are left with the newtons, which is a unit of force. That's very nice. And once you input that in your calculator, you should get an answer of 1.0005 times 10 to the negative 8 power newtons. Okay? And that value is basically the force that they are exerting upon each other. Yeah, the force of gravity acting between them, rather. It's right here. So how do we make sense of this? So we're gonna compare it to the weight of each particle. Okay, let's do it in another frame. Okay, it's kind of bright. Okay, so to do this one, it's just real simple. Let's put the weight 1, and we also have a weight 2, and this would be for m sub 1 times the gravity and the gravitational constant, gravitational force, m sub 2 times the gravitational force, as we can see right here. Okay, and we can easily do that. Just substitute some values. So we have 8 kilograms times 9.81 meters per second squared, and this is 12 kilograms times 9.81 meters per second squared. Okay, and once you input that in your calculator, you should have the answer for the first one, 78.48 newtons, and for the second particle, it's 117.72 newtons. Okay, now how exactly are we supposed to compare these values? So that would be by getting the ratio of weight 1 to the force of gravity acting between the two objects, the two bodies, the two particles, and it's the same for the second one. So let me put this here. So we can let any variable basically be the ratio, but we're gonna do phi for this one. So as we know, phi also signifies the golden ratio, so it just fits here. Let phi be the ratio. Okay, so we have again two answers for this one. We have phi sub 1, yeah, phi sub 1, and phi sub 2. Okay, and that it will be the weight over the force, weight 1 over the force, and this would be the weight sub 2 over the force. And again, we're just substituting values for this one. Okay, so we have 78.48 newtons over 1.0005 times 10 to the negative 8 newtons, and for the second one, the same denominator for the second one. Newtons, and we can just cancel the units since we're just getting the ratio. of this one, and then you can input it in your calculator, and it will give you some large values, but you can just apply the scientific notation. And for the first one, if if you can if you got the value, it would I just rounded it off. Okay, I just rounded it off for you guys to see what value is it close to. So it's 7.84 times 10 to the ninth power, and for this one, this is 1.18 times 10 to the 10th power. And let me change the equal sign to approximately, since we're not using the exact value, since we rounded off. So what do these values mean? This means that for the first one, the force exerted, the force acting, yeah, let me highlight that, the force acting on these two bodies is 7.84 times 10 to the ninth power smaller than the weight of the 8 kilogram particle. And for the second one, it's the same. The force acting, the gravitational force acting between these two bodies is 1.18 times 10 to the 10th power smaller than the weight of the 12 kilogram particle. So that's why it's kind of negligible to say that there is force, gravitational force acting upon those two bodies, but still there is a force. Yeah, even if it's minuscule, we can say that there's a force acting upon it. Yeah. And I guess that basically sums up the video. Yeah. So again, if you guys were solving with me, it's okay if you got a different answer, and even I can make mistakes sometimes. So if you notice some mistakes in my answers, of course you can just go ahead and correct me. Yeah. And I guess, yeah, that is basically it for this video. We solved these problems fairly easily, and I hope you can tune in later if I still have the energy, and I'm gonna make a video about differential equations. And yeah, what is the time? It's almost 1:30 a.m. in the morning. So yeah, I still have like 3 hours of sleep left, and I'll see you guys in the campus if you guys are going there, and you can just watch this video in your free time. And yeah, that's it, guys. Thank you for tuning in and staying with me until the end. I really appreciate it. Thank you, guys, and I will see you next time.